Anybody have any questions before I do so? Okay, I still haven't made that video for the syllabus. You can actually look up a video of a syllabus on my YouTube channel if you'd like. I plan on making the other one tomorrow. That should be more than enough, though, if you want to look at that old one, because that pretty much doesn't change from year to year. It's the same policies. I think even, yeah, that one, the version that I posted on there last semester, still has the same grading system as well. So it's still, 30% for the final exam, 25 or 25% for the final exam, 30% for the face-to-face test. So, by all means, check that out. You can just go to my YouTube channel and do a search at the YouTube channel for syllabus, and you'll probably find one of the videos popping up there. But like I said, I will be posting another one. I'll probably post it there as well. The only danger of me posting it there is I usually have my phone number, of course, on the syllabus, and I don't want that on the internet. So that's a bit of a problem. When we were last together, we were working on chapter one, and I had advised you that I would be going through all of chapter one. And basically, the first three sections were sort of sections that you're asked to cover on your own. I explained my version of the discussion about section 1.1 and 1.2, which is how science works and models, theories, and laws, and measurement and uncertainty is something I'll cover in lab. So I just wanted to remind you guys that you do need to read those first three sections, 1.1, 1.2, and 1.3. And the questions that ask about such things on the practice tests and on the homework and then on the face-to-face tests that we ultimately take as well, all of those will be based on the way the author wrote those sections. That's why I'm telling you I'm not covering it the way he covered it. I told you my version, but any questions that come up on the test will be related to the way that he explained it. So by all means, make sure you read those three sections, understand them, 1.1, 1.2, and 1.3. And every time, of course, like always, when you see a boldface term, a term written in bold type, you want to make sure you look up the definition of that word and know it at the drop of a hat. Again, I also said that about anything that the book calls a law or anything that a whole subsection or a whole chapter is named after, you should also go ahead and commit to memory verbatim and be expected that that might be a question a teacher asks in the college environment. And we think we're doing you a really big favor when we do that. So we're really, really, really trying to be nice by giving you such a question. And a lot of people just aren't getting it. They're not familiar with that sort of paradigm, if you will. So I want to make sure you guys are ready for that when you go somewhere else, as well as if I were to ask a question here. So it seems like no one has any questions. So I'm going to go ahead. When we last spoke, like I said, we had done unit standards in the SI system. I told you about a multiple, or excuse me, an extra credit problem where you could calculate the minimum dimensions of a cylinder. I also told you about another one where you could calculate the density of water in various units. Both of those are really good exercises to practice. But I also told you about the standards, what we used to use, for instance, for the standard of a meter, what we now use, what we use for the standard of a second, and what we now use for the standard of a second, that sort of thing. I did cover converting units, and I did cover dimensions and dimensional analysis. I will tell you that last night for my other online 241 class, I did another similar lecture, but some of the examples I did were a little different than the examples that I did in your class. So by all means, check them out, especially the dimensional analysis one. I did another dimensional analysis problem on that video last night, and it's different from the Planck length one that I did at the end of class last time. So this one's doing the Planck mass, and it's a little bit more complicated to calculate and solve the system. So it would be very good for you to check those out. Uh, and that's going to happen the whole semester. We're going to have usually the two classes, the 241 that meets online on Mondays and Wednesdays, will cover more or less the same stuff that meets on Tuesdays and Thursdays. But sometimes the Tuesday, Thursday class we'll get a different example than the Monday, Wednesday class. And sometimes the Tuesday one will be better. Sometimes the Monday one will be better. But the main thing is just know that that's more resources in addition to the optional videos that I give you in your weekly module. I am satisfied with only completing chapter one this week. Chapter one homeworks you should expect to be due by Sunday at 11:59 p.m. So make sure you get chapter one homework done by then. In the future, I might put the homeworks back a little bit later. The reason why I'm doing that is I notice sometimes students get overwhelmed and just miss a homework assignment or something like that. So I want you guys to go in with the mindset that every Sunday, 11:59 p.m., you will have a homework due, probably at least two homeworks due every Sunday at 11:59 p.m. So you need to make sure you get those done every Sunday, not by looking on Canvas, but by going to Canvas and then going into My Lab and mastering and seeing what's due every Sunday. Okay, so please do that. That being said, I'm probably going to push the homeworks back in such a way that they will, in some cases, not be due before you're tested on that particular chapter. So, for instance, our online test one will cover chapter one and two. I might put the date of homework chapter two. I might put the dates that that's due later than the date that the online test is due. If that's the case, you would be crazy not to have tried your homework before you took that test. But I want you to treat the homework like a learning experience. So what you want to do is when I cover chapter two, and have already covered chapter one, you should immediately start taking your practice or your practice exam or your practice test for that online test as well as for the future face-to-face test. And when you start doing that practice test, if you run into problem solving problems that are on it, then you want to go back to the homework and look for one of the tutorials that might be closely related. And then that can help you because that is sort of the purpose of me using that online homework system is a lot of the problems are very instructional. All of the problems are experiences that you need to experience so that you learn how to solve physics problems. But some of them are literally called tutorial problems where they walk you step by step through a problem solving technique. So I want you to go back and forth between that and your practice test to learn how to solve physics problems. If you're just looking up answers on your practice test, or if you're just looking up answers on your homework, you're really going to come out in a bad way at the end of the semester, or maybe even by the first test. So just don't do that. Try to use it all as a learning experience. And as I told you before, don't focus on trying to get a perfect 100 on your homeworks. Try to shoot for somewhere between a 78 and a 85 as the bare minimum. If you can maintain that, I promise you by the end of the semester, you'll see a way of making your grades in the course be positively affected or at least not negatively affected by your homework. Okay? Any questions now that I've said all that additional stuff, some of which I said last time, but not all? Okay. All right. Well, we're starting now with the remaining section of chapter one that I didn't cover, and this is called Order of Magnitude Rapid Estimating. Uh, this is actually what we often term Fermi or Fermi. It should be pronounced Fermi, as far as I know. Fermi calculations. There was a guy by the name of Enrico Fermi. I have a biography of his around here somewhere. It's really a good biography. It was called The Last Man Who Knew Everything. He was the kind of guy that you just talk to and like you would say something like we all do, just randomly throwing a number out there, taking an estimate of it. And he would say, "No, I don't think your number's quite right." And he would literally do the calculation in real time and tell you what your number is. And it would be about anything, about stuff he didn't know about. Like one time, he asked his students how many piano tuners there were in the Chicago area, and he quickly did a calculation for all the students, and then they went back and sort of looked into it and found out that he was right on the money. That's the kind of calculations you should be able to do when you complete a physics course in some sense. He had a vast knowledge of everything. He was probably someone that would have been really good on Jeopardy and that sort of stuff too. But the main thing was Enrico Fermi. He was the person that created a physics department in Italy under Mussolini, and before Mussolini, he had started becoming really good as a physicist. In fact, he taught himself physics from a Latin physics textbook. That's kind of crazy, but literally had a physics textbook written in Latin that he found in a library when he was like 7, and he worked his way completely through that before he was even 10 years old. He just was a brilliant, brilliant person. taught himself languages, knew something about everything basically, and he basically made the physics department so great that it was the pride of Italy, obviously, and in fact, it was one of the greatest in on the planet. And he managed to win a Nobel Prize. He could have won probably 12 Nobel Prizes, to be honest with you, for all the work he did. But when he won the Nobel Prize, he used that as a arguing point where Mussolini wanted him to go accept the Nobel Prize so that Mussolini could tout his brand of, socialism as the greatest government there is and that sort of thing. And Enrico Fermi said, "Well, okay, yeah, I would love to go, but I want my family to go with me." And he said, "No, we can't let your family go with you." So he said, "Okay, well, then I'm not going." So finally, they went ahead and said, "Well, we really want you to get this award, and we really want to get the pride that comes from it." So he went ahead and agreed for Enrico Fermi and his family to go to America, or excuse me, to go to Switzerland to accept the Nobel Prize. And when he did so, he went ahead and defected to America. That's why we have Fermi Lab, and we have Fermi Lab up in Illinois and stuff like that. He was a professor at the University of Chicago, which is one of the most rigorous universities on planet Earth, much less in America. And he is the first person that made a sustained nuclear reaction. He did so under the football field of the University of Chicago stadium. And he also did a lot of other things. For instance, he was a very, very, very important part of the Manhattan Project, and in fact, he appears in the Oppenheimer movie. If you see the one part where they're doing the Trinity test, and you see this guy drop some dust and grass clippings or whatever, that guy is Enrico Fermi. And what he was doing when he did that is basically he realized that he could calculate the yield of that atomic bomb just by dropping dust particles and seeing how much they moved forward and backwards as the pressure wave from the nuclear bomb went off, and then knowing the distance away that he was from it, he could work it out, and he ended up estimating exactly what the yield of the weapon is, and was within a couple percent of what the ultimate calculation showed. So that's just the kind of awesome dude he was. So anyways, that's what these calculations are. They'll seem kind of odd, but that's the last section we're doing with chapter one. I may start into chapter two just to make it a little easier, but it all depends on how much time we have. So, the first problem we're doing in section 1.6, order of magnitude and rapid estimating, is example 1.5. And actually, it's taken me a little while to get my iPad to turn on for some reason. But as soon as I get that turned on and everything, I will do it. What the problem says is estimate how much water there is in a particular lake, which is roughly circular, about 1 kilometer across, and you guess it has an average depth of 10 meters. So that's one of the things we often do in physics is obviously we would never expect to find a perfectly circular lake, but if the lake looks mostly roundish, then why not treat it like a circle? Because we happen to know a very easy formula for calculating the volume of or the area of a circle. And then, of course, if we treat it as if it's a cylinder, then we obviously know a very good technique to calculate the volume of a cylinder. If it wasn't actually even remotely circular, then what we could do is divide it up into circles and squares and stuff like that, and then you calculate the surface area, and then if you assume the depth has some average depth, then you could treat it as if it's basically that shape, which would be circles and squares and all that stuff, but with straight vertical walls down to a flat bottom, and you could calculate that way to figure out the volume of it. So that's pretty much what we're going to do. Before I do that, though, I'm going to go ahead and change my file that I'm using to the appropriate date. Today is the 20th. So I've got to change it from 519 to 520, and it's PHY 241, and it's not N01B, it's O01B, and that about does it. So I now have the file made up, and I can now go ahead and try to share my screen. Let me do that with you real quick. So I'm going to share my iPad screen. And that should pop up any second now. Feel free, like I said, ask me questions at any time. You can type them in via the chat if you'd like. I do try to always have that chat window open, but sometimes I don't see it down there at the bottom. So by all means use that, but you're also just welcome to blurt out the answers. That's not a problem at all. Let's see if I can. I was trying to see if I can actually change this window to a more a more square shape instead of such a rectangular shape, but it looks like that doesn't work. So here's my first example. Example 1.5. Your book says one dash, but I don't care about that. Uh, so as we said, where we are assuming or estimating or approximating that this lake is approximately round with a average depth they specifically said was 10 meters. So I'm going to say D is equal to 10 meters. And we also said that the distance across the lake was approximately 1 kilometer, like this. Okay. And now what we're asked is to estimate the volume of the lake. So V lake is equal to question mark. So not only is this a perfectly reasonable question, I would tell you that part of what we're trying to do with these questions is we're trying to get you guys to learn what the metric system looks like. So we want you ideally to actually think in terms of the metric system. Like, for instance, when you look at the road, do you think the road is like 30 feet wide, or do you feel like it's more like 10 meters? We would rather you say, no, that feels more like 10 meters to me. Obviously, if you didn't grow up, if you grew up in America, that's not going to be an easy thing. But if you grew up somewhere else, it'll be a little easier. But you should get very proficient with that. That is part of what you're learning in this course, and it is part of what we're testing. So we expect you to be able to, for instance, look at this book that I'm holding up right here, and looking at this book in the presence of my hand and various other everyday life things, you should be able to estimate how thick those pages are. In other words, how thick is the distance from the bottom edge of the cover to the top edge of the back cover. In other words, how tall is that stack of paper? That's a very common thing that I'd want you to be able to estimate in centimeters. To do that, I want to tell you that a centimeter, at least for a person my size, a centimeter is about as long as my pinky nail is wide. So if you look at your pinky nail, that's usually your thinnest fingernail. And if you measure it from your skin on the left hand side of your pinky nail to the skin on your right hand side, you can assume that's approximately 1 centimeter. A millimeter, on the other hand, is 1/10 of a centimeter, and it's hard to think of it in terms of that way. But what I'd like to tell students is if you've ever seen a heavy duty staple, they're normally a little thicker than regular staples, but that thickness of that heavy duty staple is normally about a millimeter. A regular staple is probably a little bit less than a whole millimeter in thickness, but I'm just talking about the thickness of the metal, not the distance from the staple that goes up, over, and back over. I'm not talking about that. That's more on the order of a centimeter, but the thickness of that metal is usually on the order of a millimeter. I would say if you've got a grandparent or an older parent or something like that, you might look at one of their big toenails and you probably estimate that to be about 2 millimeters because they're usually pretty thick by the older we get. So that's another thing to use. A meter itself is about 39 and 1/8 of an inch. I would tell you that a meter is about the height of a doorknob. So if you measure from the floor up to about the top of a doorknob, that's about 1 meter as well. So I want you guys to be able to look at like a room and say, how big is this room? Is the width of it closer to 5 meters or closer to 6 meters? Is the height of it closer to 3 meters or 2 meters or 2.5 meters? That kind of stuff. Uh, and the width as well, all that good stuff. So that's something you can do. That being said, there's also another way you can do it. So if you can't estimate very well exactly how big a room is, what you can do is try to say, well, I know for a fact that it's bigger than blah. And you could say, I know for a fact it's smaller than blah. So if you look at a wall in a room and you say, okay, well, I know that 10 meters would be like 34 feet or something like that, and that doesn't look as big as that. And then you look at a wall and you say that, well, 1 meter is only about 3 feet, so I know it's bigger than that. If that's as close as you can estimate it, I'd say I'd call BS on it for starters, but even if you did, it's okay. What you can do is take what we call the geometric mean. So if you know for a fact it's bigger than 1 meter and you know for a fact it's smaller than 10 meters, then take the product of those two and then take the square root of that. So 1 meter times 10 meters is equal to 10 square meters. Take the square root of that and you get approximately pi meters. That's another trick that Larry Weinstein taught me. He wrote a great book called Guesstimation 2.0. He wrote another one before that just called Guesstimation, but he's a faculty member at ODU. And I think he might be emeritus now, but he's definitely mostly retired, but he's still, very active person. So that's another technique. So whenever you're trying to estimate the size of something, try to find the smallest number that you know it's bigger than, and then try to find the biggest number that you know it's smaller than. Uh, and then just take the geometric mean of the two by multiplying them and take the square root. Okay, so that's another way you can do it. So with that being said, we're now going to calculate roughly the volume of this 1 kilometer large lake that's approximately 10 meters deep on average. So the volume for a cylinder is equal to pi r squared h, or in this case, pi r squared d, since I called the height d, since it was a depth. Now the r would be half the distance across, so we're going to call that half a kilometer. And what we're going to do is say this is approximately 3.14159. But when we're estimating, we really don't choose to use that many decimal places. What we normally do is we can use that many decimal places in the numbers we put in, but we're ultimately just going to round the answer to one sig fig, because that's what we're meaning when we talk these rapid estimations. We really want to know what we call an order of magnitude. So what we care more about is not the mantissa of the number in scientific notation, but the power of 10 of the number in the scientific notation. The mantissa is the little number that goes out in front of times 10 to the power. That's that part of the scientific notation number. So like 4.75 times 10 to the fifth. The mantissa is 4.75, and the fifth is the power of 10. That power of 10 is really just as important. That's more or less what we're looking for. We don't care so much about the mantissa, except the mantissa to one sig fig. Okay? So 3.14159, we're also going to say zero point 0.5 kilometers, but I don't want to use kilometers. I want to know it in cubic meters. So I'm going to say 1.5 times 10 to the third meters is the radius. And then I'm going to say the depth is 10 meters. So we get pi r squared times 10. And in this case, if my calculator would ever turn on, that would be super helpful. Okay, so I'm going to take 3.14 times zero point 0.5 times 10 to the 3. And now I'm going to take that number and square it. And now I'm going to take that number, all of that, and multiply that by 10. So if I multiply pi times 0.5 times 10 to the third squared times, and actually I don't like this calculator I'm using, it's becoming a nuisance. I'm not even sure it's doing what I want it to do. Yeah, I'm using a different calculator than I normally use, so I apologize. I'm going to have to regroup a little bit for a second here. And now I'm going to square that. And now I'm going to multiply that by 10. Sorry about that taking so long, but hopefully you already have an answer. I got 7.85 times 10 to the 6, and that's cubic meters. Now that 7.85 is a lion's share of the way to 10. So what I'd say is the volume of the lake is of the magnitude of 10 to the seventh cubic meters. Okay. You might want to call it, for instance, just 1 times 10 to the seventh cubic meters. That would be fine as well. But I'm doing this specifically because I know for a fact when you go to do these estimation problems in the online homework, it asks you for some of those, and several of my students don't get it. But in this case, if they'd actually asked you for this problem, the answer they're asking for is not 10 to the seventh. It's not 1 times 10 to the seventh. They're literally just looking for the 7. Okay, because that's the order of magnitude. That's the power of 10 that you have to multiply by cubic meters to get the rough volume of this. So just keep that in mind. Does everybody follow what I did there? The volume of the lake is about 10 million kilometers, or excuse me, square cubic meters, I should say. No questions on that? And that's what the book has. So you can also then use that to estimate how many gallons you want. And sometimes it's really smart to use really good answers. Nathan, was that a thumbs up or was that a hand raised that I just saw? Okay, I think you just gave me a thumbs up saying that, or maybe an okay symbol. I saw just the yellow text out of it. Oh, all good, cool. All right. So this is the answer. And like your book says, to express our results in U.S. gallons, we see the table in the inside front cover that 1 liter is about 10 to the negative third cubic meters, and that's about 1/4 of a gallon. So if you divide this by 4 times 10 to the negative third, you'll get 2 times 10 to the ninth gallons of water. So that's how you could get that. But when I was telling you about sometimes it's really smart to use units, one of the units that I ran into when I was doing when I was doing civil engineering work, I was choosing to do structural engineering, but most of the work I had to do was land development and wastewater retention and stuff like that. Also, treatment of wastewater because we don't have septic systems. We don't actually have a sewer system in the Outer Banks, which is where I was working. So everybody has either a septic tank or some kind of fancy septic system, and we would have to engineer those. So one of the units that I discovered that was really awesome was the inch acre. Has anybody ever heard of an inch acre? Okay, that's kind of a neat little thing because what you have to do when you're actually in the business of building commercial properties, you're often going to take a large chunk of land and you're going to cover it with an impermeable surface with, concrete and asphalt, for instance. And water when it rains is not going to soak through that. It can't just soak through the concrete, so it has to be funneled off to keep the place from flooding. And not only that, the law requires that when you build such a premise, then all the water that happens in any storm has to be accounted for and taken away without running it onto your neighbor's property. So that's a really big deal. So what we would do is, for instance, at the Home Depot in the Outer Banks, I know the building, for instance, was 110 square. It was actually 110,000 square feet was the building itself, and then the parking lot was about another 400,000 square feet. So we ended up having about 500,000 square feet. An acre is 43,560 square feet. So you could basically figure out by taking the 400,000 the 500,000 and dividing it by 43,560, that would tell you how many acres there are. And then the job was you've got to look up the 50-year storm data because that's what the law requires. So you look up over the last 50 years. They actually have tables for this. You don't have to literally look at every year and find the worst, but you look up the 50-year worst storm that we had in that area in the last 50 years, and it turned out to be like 3.8 inches was what was done, or 7.9 inches was what was gotten in the worst storm of the last 50 years. So our job then was to find somewhere to take all of that water. So 7.59 inches times however many acres of land that's impermeable, that would naturally give you a unit of inch acres, because you're taking the acre, which is the square footage, multiplied by the depth, which is in inches. So it would automatically give you exactly that value. Then what we do is build huge, or dig huge ponds around it. That's why when you go to a mall or a shopping center, you'll inevitably see not only big ditches around, but you'll often see ponds like the one around the Home Depot, for instance, off of Battlefield Boulevard near the North Carolina line. There's a huge pond in between it and the Wendy's and the Taco Bell and the I can't remember that other restaurant that's there. But anyways, there's Taco Bell too. But that big pond is responsible for catching all that water. I suspect it was initially from Home Depot, but it also became part of what they're using, I think, for the Hardee's, uh, and the Home Depot. I mean, the Hardee's, the Wendy's, and the Taco Bell as well. So that's what that pond's actually for, and you're responsible for doing that. So not only do you have to have a storage place where that can fill up without running into the adjacent properties, but you also have to have a piping system that can get it there. So that's just some of the kind of stuff that you do as an engineer, specifically in the civil engineering realm. Let's look at another example. This is example 1.6, but I'm doing it a little differently. Example 1.6 for my book. Estimate the thickness of the paper on which it is printed. So that's our problem. I want you to estimate, looking at this book right here, I want you to estimate how thick a single page of this paper is. Okay. So you're looking at this book right now, and I'm going to tell you that the total number of pages is 750. Okay. It has 750 pages. And I mean pages counted like a regular book page. So when you're looking at a page, there's page one right here, and you turn it over, there's page two on the back side. So that's something important that you got to take into account. So, in order to do this, I've sort of already hinted at what you do. So, can anybody tell me in centimeters roughly how tall this white chunk of paper is from the back cover to the front cover? We're not counting the thickness of the cover, so we're not counting this thickness and this thickness. We're just trying to count the thickness of the whiteness that you see. Anybody have an estimate of how big that is? You'll notice it is also about the size of my glasses. So you might have a sense of how big those glasses are. These are Oakleys. They're not that huge of a variance from one pair of Oakleys to the next. Anybody estimate how many centimeters? Someone says 3 to 4 centimeters, 2.5. All of those are pretty good answers. It's actually right at 4 centimeters, is what I would estimate it to be. But again, if you didn't know that, what you could do is say, I know for a fact that that's way bigger than a centimeter, because there's my pinky right there. And then I could do like this and this. And I know very much so that it's smaller than 6 centimeters. So what you could do is take the geometric mean of 1 centimeter and 6 centimeters. So 1 centimeter times 6 centimeters is 6 square centimeters. You take the square root of that, and what you get is, my calculator just likes to turn off really rapidly. I'm going to calculate the square root of 6 now, and that's about 2.5. So you could use that. I'm going to go ahead and go with the 4 centimeters that I estimated. So I estimate our solution I estimate that the stack of pages is about 4.0 centimeters tall. And since the number of pages in the book is 750, that would mean I also estimate the number of pages of paper is about 375. Notice 350 is half of 700, and then 25 is half of 50. So half of 750 is about 375. So that's really how many technical paper pages there are. So the thickness of a page, delta, let's say delta T equals the thickness of the paper, is going to be equal to the thickness of the stack divided by the number of pieces of paper. And I'm trying to say pieces of paper because if I said pages, that would make you again think 750, but it's not 750, it's 375. So what that means is I'm going to take 4.0 centimeters and divide it by 375, and I'll get delta T is equal to 4 divided by 3.75 equals, oh, excuse me, 4 divided by 375 is equal to 0.011 centimeters. So that is basically 0.11 millimeters, and really we would say delta T is on the order of zero point 0.1 millimeters. Again, 1 sig fig is what's relevant there. And in this case, if I asked you for it in meters, you would say it's 1 times 10 to the negative 4, or you would say delta T is approximately 10 to the negative fourth meters. And in the way that the online homework system is asking you for a couple of these estimates, you would just type in negative 4. Does that make sense to everyone? Okay. Here's another estimate. Now, what I'm trying to think here is something that everybody, I know what I can do. This is going to be example, and this is just one I'm making up. Approximately how many soda cans can you fit in a small dressing room with a normal height ceiling? Okay, so there's a estimate. One of the ones I've done in the past is, for instance, in the classroom that I'm giving the test in, I would actually, this is one that my master's advisor asked me when I was taking this same course. He said on our very first test, how many fruit flies could we fit in this classroom? And the classroom was huge. It was like, 35, 40 feet wide. I'm telling you in feet for a reason, and like 65, 75 feet long. And of course, the ceiling was about 3 meters high. So we had to estimate that. And that's what we were asked to do. He didn't tell us those sizes of the room, and he didn't tell us how big a fruit fly was. And what he looked for was what was our estimates for the sizes of the fruit fly and what was our estimate for the size of the room. And that was possibility for us to lose points. And then we had to figure out a way to figure out how many flies we could fit in there. I've seen TikTokers do the same thing where they try to fill up a shower stall, for instance, with Fruit Loops or something like that, or Apple Jacks. It drives me crazy because I'd watch it and I'm like, this person's driving a friggin' Lamborghini because he's made so much money on these stupid videos, but he ain't smart enough to figure out how many boxes of Fruit Loops it takes to fill up a shower. It's like a 2 second calculation. So he ends up going to the store like 3 times. So, anyways, that's the kind of calculation you should be able to do. So, anybody want to estimate or what you think is an estimate of the size of a room? I'm specifically talking about three dimensions like width of the room, depth of the room, and then the height of the ceiling. And when I say it's a normal height ceiling, I mean it's typical for what you'd see like in a house as opposed to like walking into Walmart and you see the ceiling's like 30 feet high or something like that. I'm not talking about that. I'm talking about just a regular room that might have somewhere between 2.5 to 3 meter high ceiling or something. So anybody make a guess as to how big, what the dimensions of a changing room would be? So I'm gonna say, yeah, 10 feet by 12 feet. I'd say that's a little big. It sounds like you've been going to Kohl's or something nice like that. I'm talking like Walmart, where it's like, maybe a meter by a meter, or maybe a meter and a half by a meter and a half, and then maybe 3 meters tall. But you've got the right idea, so that would be acceptable. Again, I want you thinking in terms of meters, not feet, though. So in that case, I would probably think along the lines of maybe 3 meters by 4 meters. Okay, in this case, what I'm going to say is approximately, let's just call it 2 meters by 2 meters. And the reason why I'm saying 2 meters by 2 meters, I was really leaning towards about 1.5 meters because it's a little bit bigger than 3 or 4, almost 4 feet or something like that. So I'm going to say 2 meters by 2 meters. That gives me roughly, 5.5 feet or something like that. 2 meters by 2 meters, and then I'm going to say the height of the ceiling is probably about 3 meters because that's a little bit more than a 9 foot ceiling. So that's the dimensions of the room. Now I need the dimensions of the soda can. So the dimensions of a soda can in this case, a soda can's about this tall. I'm going to go with that being about 12 centimeters. And the diameter, I would say, is probably on the order of 5 centimeters. So I'm going to say the soda can would look roughly, I'd said about 12. I'm just going to go ahead and call it 15 centimeters. And I'm going to call this distance right here about 5 centimeters. And that's pretty good. Okay. That's what I'm estimating my soda can to be. Now, if you said 50 centimeters, then obviously you get it wrong. If you said 5.5, I wouldn't have a problem with it. If you said 4.5, I'm not going to have a problem with it. If you said 4, I wouldn't have a problem. If you said 6, I probably wouldn't have a problem. It's more when you get maybe a factor of 2 or 3 larger than what the real estimates that I make are what I would actually measure to test. If you're off by that far, that would start to make me think that maybe you didn't understand it that well. Okay, so what I'm going to do is imagine that I can just make this representative of or represented by a rectangular shape. I'm going to say the rectangular shape is approximately 5 centimeters by 5 centimeters by 15 centimeters. So what I'm going to do is say the number of cans. Oops, went the wrong one. The number of cans is approximately equal to the volume of the room divided by the volume of the can. So this is approximately going to be the volume of the room is 2 meters by 2 meters by 3 meters, and the volume of the can is going to be 0.05 meters by 0.05 meters by 0.15 meters. That's going to give me 2 times 2 is 4 times 3 is 12. So that's 12 cubic meters divided by 0.05. Let's turn this stupid thing on again. 0.05 times 0.05 times 0.15. And this gives me 0.000375 cubic meters. So I'm going to say 12 divided by that answer. Actually, my pushing of the division symbol was not hard enough, so I had to go back and do it again. So 12 divided by that answer is about 32,000 cans. So I would say the number of cans is approximately equal to 3 times 10 to the fourth cans. Everybody follow that? Some other ones that you might think of is a typical shoebox. How many pennies can you fit in it? Or, as I said, how many fruit flies can we fit in this room? Now, fruit flies, I'm talking about those are the little house flies. So, if you're thinking about a fruit fly, you probably think that its body is maybe, I don't know, 3 millimeters tall, 3 millimeters wide, and maybe about a whole centimeter in length, or at least maybe point 0.5 centimeters in length. So you could treat it like a little rectangular solid that way, and then just assume they're all going to be stacked up kind of neat. So you divide the volume of the room by the volume of the flies. The main thing is when you go to calculate something like this by dividing the volume of the room, for instance, by the volume of the flies, or the volume of the room by the volume of the cans, you got to make sure they're in the same units. If you're not doing it in the same units, it's going to make a big mistake. Okay. Now, when you do this, most of the time it'll be in the practice test, you'll have multiple choice. And basically, they won't have an answer like for this one, they wouldn't have 3 times 10 to the fourth and 4 times 10 to the fourth as both answers, because both of those would be acceptable, but they would have 3 times 10 to the fourth, they'd have 3 times 10 to the fifth, they'd have 3 times 10 to the third, and they might even have something really off the wall like 3 times 10 to the eighth and 3 times 10 to the negative 2. Okay, so it'd be more about finding out roughly what it is. If you're within a factor of 10, it's good. Now, when I do it when it's not multiple choice, then it's a matter of me looking at your approximation. So you'd really want to write size of room and then tell me what you're thinking the size of the room is in meters or centimeters or whatever you want. If you have to first do that in inches or feet or something like that, that is perfectly fine. Then you have to do the extra step of converting it to centimeters, because I don't want to see any calculations done in cubic meters or cubic feet or cubic inches. All the calculations definitely have to be done in centimeters, meters, millimeters, that kind of thing. Everybody follow that? All right, here's another example. This is example 1-7. In this one, it says height by triangulation. And they have a little picture of a person standing, and then they have the ground, and then they have a tall building, and then they have the ledge. And what we're doing is we're looking up at the height of the building. And what we've done is managed to align that line of sight with a sign. So this is our particular sign, for instance. It might say, Duke sucks. Because that's what the sign's going to say. All right. Uh, and what you do is, according to the textbook, the height of the sign is 3 meters, and the distance you are away from the sign is 2 meters. And what they want you to do is estimate the height of this building like that. So it says estimate the height of the building shown in figure 1-9 by triangulation with the help of the bus stop and the bus stop pole and a friend. That's not a bus stop toll. That's a sign advertising the greatness of the Carolina Tar Heels. That's what that is. That's not a bus stop sign. Okay. All right. So here's the big trick. What we see right here is, oh, also they gave you this. They were kind enough to tell you this. I wouldn't have done that. I would have had to make you figure that out, and I'd also take off points if you didn't account for it. But what they're telling you is that this person's eye height is about 1.5 meters. Okay, so you can make a triangle, in other words, and that's what they're wanting you to do. But then when you make that triangle, you're going to find the length of that opposite side, which I'll call X, say, and then you're going to have to add to it 1.5 meters. Does that make sense to everyone? All right. So the way you do this is as follows. We actually have a similar triangle. One triangle is 2 meters by 3 meters, but because that line of sight goes from your eyeballs across the edge of the top of that sign, then that line of sight also goes to the top of the building. So the triangle that is made by your eyeballs, the 1.5 meters up the side of the building and the top of the building, that triangle is a similar triangle. We also do not know necessarily yet exactly how far this is, how far the pole is from the triangle. I mean, from the building, but we can figure all that out, because what we know is that this 2-3 triangle tells us that it's going to have a hypotenuse of 2 squared plus 3 squared. That's 4 plus 9, which is 13. So it's the square root of 13 for this edge right here if we need it, but we probably won't. Now, in addition to that, we have a distance I'm going to call W for the length of that part of the triangle, and I already drew this distance as X. That's why I ended up calling that other one W instead of X. So what we know is 3 meters is to 2 meters. This is always what happens when you have what we call similar triangles. 3 meters over 2 meters corresponds to what 3 meter dimension on the small triangle, what does that correspond on the bigger triangle to? Does it correspond to the W or to the X? Can y'all figure that out? When the triangles are stacked like this, where they're actually one is inside of the other, then sort of parallel sides are similar sides. Exactly, Mihak. So the 3 meter corresponds to the X, and the 2 meter corresponds to the W. Okay. And I think they did not tell us that W, did they? Find the height of the building shown with the help of the triangle. Gotcha. I think, yeah, okay, they did give you the diagram. So they also were kind enough to give us this distance, which was super helpful. So this distance was given to us. I apologize. I didn't see that on the diagram. I was trying to figure out how I was going to get it. But they're saying that this distance from the person all the way to the building is 18 meters. So we do actually know W. So now I can erase that W down there and put 18 in it. And what we see is 3 meters is to 2 meters as X is to 18 meters. So that tells us X is equal to 3 meters over 2 meters times 18 meters. We know that 18 divided by 2 is 9, and then 9 times 3 is 27. So we get that X is 27 meters. Now, that is just the height from the line of sight or from the height of the eyeballs up to the top of the building. So we have to say that the actual height of the building, H, is equal to 27 meters plus 1.5 meters, which equals 28.5 meters. So that's our estimation of the height of the building. Did I do something? Oopie doo. Oh, 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 oh. Everybody notice what I did? I just realized I made a boo boo. Anybody see it? Notice the height of the sign. And now notice the height of the eyes. I forgot to take that into account. So the inner triangle is not 2 meters by 3 meters. So let me fix that real quick. Sorry about that, everybody. That's just a boneheaded mistake that I made. Sometimes I make it just because I'm talking while I'm doing stuff, and it's so easy to lose attention span of what you're doing while you're talking out loud. I can't even read out loud. When I read out loud, I literally can't remember anything. So, in reality, what we have here is the triangle is not 2 3. It's actually 2 1.5. So sorry about that, everyone. Now we got it. Notice I knew it's 1.5 because the height of the eyes are 1.5, despite the scale of the drawing, which obviously is way the heck off. But that leaves only 1.5 meters above the horizontal eye line. So now we're going to say 1.5 meters over 2 meters is equal to x over 18 meters. That means x is equal to 1.5 over 2 times 18 meters. 18 divided by 2 again is 9. 9 times 1.5 is 13.5. So we get 13.5 meters is x, and that means that H is going to be 13.5 meters plus 1.5 meters because that's how high my eyes are, or the eyes are the person are. So this is going to be a 15-meter tall building, not a 28.5 as I made a mistake a second ago. Any questions on that one? Sorry about screwing up on that 1.5. I should have been paying more attention to what I was doing instead of what I was seeing. And that's what they got was 13.5. I didn't see that answer yet, but I knew as soon as I looked up here at the second diagram, I saw the 1.5. That's what told me that it was that I was wrong. Any questions with that? All right, the next one is kind of neat, and you'll see some of these in your practice test. This is example 1.8. And this one it says, estimate the total number of beats a typical human heart makes in a lifetime. Okay. So what we have to do in this case is I need to estimate on average how many times a heart beats every hour or every minute or every second or something like that. And then I need to figure out how long is the average human life. So we expect you to know a little bit of stuff about nature and reality and stuff like that. So it's not unusual for us to expect you to know the total number of people on planet Earth. And it's also not unusual for us to expect you to know the total number of people in the United States. Okay. Can any of y'all tell me the total number of people on planet Earth? Just, order of magnitude, maybe? Yep, 8 billion. 8 billion is a good number. It's roughly somewhere between 8 billion, 8.5 billion, something like that. Absolutely. Far as people in America, that's on the order of about 370 million now. So 370 million is another number we expect. 8.142 billion. Thank you, Mihak. Yeah, and on a test situation, you're not able to Google stuff like that, right? But it's good to check. You make an estimate of what you think it is, and then Google it and check it. And that's how over time you'll learn stuff. There used to be this really great thing called the CIA fact book, but the government just decided, our president just decided to get rid of that this year, which is kind of a shame. But it's this really huge compendium of all the information that the CIA and the experts in the CIA and the State Department have put together on all the nations on planet Earth. So they have things like what's the population of each country, what's the major language, what's the major languages, what's the area of each of those countries, what's their major religion, all that stuff. It also has the SI prefixes. It has the names of numbers. Like, for instance, there is literally a number called a quadrillion, and it would tell you exactly how many number or how big the number 1 quadrillion is. So not only do we do billions and trillions, we go farther than that. And the CIA fact book gave us that. You could probably still find an old copy online. It's a huge document, and they update it every year, but they're not going to do it anymore. So if I was you, I would go find the CIA fact book and download it once and for all before it disappears. I hope a future president might bring it back because I really have used that a long time. It gives you a lot of information that's helpful. So what I'm going to go with here is we always pretend the human heartbeat's supposed to be 60 beats per minute, but the reality of it is most of us, if we're walking around or even sitting down, we'll find that when we're sitting there, our heart rate's probably on the order of 68, 70, somewhere around there. So I'm going to say the heart beats about 70 times per minute. And I'll say the average American lives about 75 years. Okay. That's a pretty good estimate. We're around the order of 73 to 70 to 75, something like that. Women tend to live a little longer than men, but not by a whole lot. If you go to some other countries, they have a larger estimate around 80, 82, stuff like that. But we'll just say it's roughly this. So the number of beats total would equal the number of beats oops, number of beats per minute times the number of minutes in a year, or I'll say number of minutes per year, so the year will be in the bottom, times the number of years we live. So, number of beats total is approximately equal to 60 beats per minute times 60 minutes in 1 hour times 24 hours in 1 day times 365 days per year times 75 years. So that's the math I'm doing. So I'm going to take 60 and I'm going to multiply it by 60 because that's a numerator. And I'm going to multiply that by 24 because that's also in the numerator. And I'm going to multiply that by 365 because that's also in the numerator. And then I'm going to multiply that by 75 because that's also in the numerator. And then I see that all my denominators are 1, so I'm just dividing it by 1, so I need not do anything at all. And now I say enter, and that gives me 2.4 times 10 to the ninth. So the total number, total heartbeats, is on the order of 2 times 10 to the ninth, or 2 billion. Any questions on that? You didn't necessarily use it here because I had the number of beats per minute as opposed to the number of beats per second, which would have been a nasty number. It'd been like 1.02 or something stupid like that. But just as a rule of thumb, here's another question. I'm going to call it an example, but it's really just me taking the opportunity to teach you a little piece of information that you can use in an approximation. So I'm going to say example. This one is not an estimate. It's actually an example. How many seconds are in a year? Okay, so this is something you can readily calculate, but I'm going to show you that it's actually a really nice number that we can easily remember. Specifically, it's pi times 10 to the seventh. There's approximately pi times 10 to the seventh seconds in a year. So pi times 10 million. Let me show you how that works. So 1 year is equal to 365.24 days. And we know that 1 day is equal to 24 hours. And we know that 1 hour is equal to 3,600 seconds. So that's going to give it to us. So now if I do this math, I take 365.24 times 24 times 3,600, and I get 3.156 times 10 to the seventh seconds. So the number of seconds per year is approximately pi times 10 to the seventh seconds. So that's a useful number that you can use from time to time. For instance, one of the things that we do in astronomy, for instance, is there was this really awesome photograph taken. Uh, we did it with the Hubble Space Telescope very early on. We focused the Hubble Space Telescope, which orbits around the Earth, we focused it on a particularly dark part of the sky in the constellation of Ursa Major. So we literally looked at what we thought was one of the darkest spots in the sky that was in fact right over the pole of the Earth or the rotational axis of the Earth, so that way we could keep the Hubble Space Telescope pointed at it at all times. If it was somewhere, lower, like aligned with the equator of the Earth would get in the way, and we wouldn't be able to keep the camera open long enough to see it. So what we were looking at was a really, really small part of the sky that looked pitch black. And in fact, the original one, the Hubble Deep Field, which is not nearly as fine as the Hubble Ultra Deep Field, but it was approximately area of the sky that was about as big as this hole in my wedding band. You see my finger fitting through it? If you imagine taking that wedding band and putting it on the railing of the pier, the end of the pier off like 17th Street or whatever, and then you imagine standing out on the actual Atlantic Avenue, that's the cone of vision that the Hubble Space Telescope was looking at. It was basically a point on Atlantic Avenue that opened up to the size of this wedding band at the end of that pier. So it's a very, very small cone, very, very long cone, but very, very small. That's how small of an area they looked at. And when you look at it, it's pitch black. Like you don't see a single star in it or anything. But what they ended up doing is they took that photo and they left the lens open. They left the film to be developed, if you will. It was actually electronic, so there was no film being developed. But they left it open for the equivalent of 11 days. And when they got, and Google this at your earliest convenience, just Google the Hubble Deep Field, and you'll see a really cool photo. When you look at that photo, what you see is a few things that have these little X's on them, like this, and all the X's are parallel. So it's like they're up and to the right and up and to the left, like that. They have these little X's on them. All of those things are actual individual stars. Everything else you see is a galaxy. Now, with that, they counted the number of galaxies in that photograph and they said, okay, that is what we thought was sort of the darkest area of the night sky. So, however many galaxies we see in that little cone, that should be a fairly conservative estimate of the number of galaxies we'd see in every cone that side. We expect maybe it'd be even bigger because a lot of the other spaces that we look in space are not that black, right? So they said, all right, they calculated that. I think it was on the order of 800 galaxies that they saw. And then they said, all right, if we wanted to surround our whole person by a number of cones, just like that cone that went from Atlantic Avenue to my wedding band, how many of those cones would it take to completely encompass us 360 degrees both ways? Well, you do that calculation just by taking the number of angled degrees in the whole sky, basically 360 this way, 360 that way, and then you multiply that times the number of galaxies in that one cone, and what you end up getting is 10 to the 11th. So there's basically 100 billion galaxies in the observable universe. That's how many stars, or excuse me, that's how many galaxies there are in the observable universe. What we mean by the observable universe is the universe, as best we can tell, was created in a what we call the Big Bang about 13.5 billion years ago. So light has only had the ability to travel for 13.5 billion years. It's actually a little bit less than that because it was completely black for a long time right after the Big Bang occurred. But either way, that's roughly what we're saying. So the most distant galaxy we can see is only a galaxy that's 13.5 billion light years away from us. It's only had that much time for the light to travel, so we can only see that far away. So if you imagine a sphere centered on us that has a radius of 13.5 billion light years, then that is the observable universe. And what we found was there was 10 to the 11th or 100 billion galaxies in that observable universe. Now, you can take some other data and figure out that on average, the typical galaxy has 10 to the 11th stars in it. And if you have 10 to the 11th stars in a typical galaxy and you have 10 to the 11th galaxies in our universe, in our observable universe, that means we have 10 to the 22 stars in the observable universe. That's one followed by 22 zeros. Now, that is just huge. In fact, it's so big that the number 10 to the 11th, remember, we just figured out that the number of seconds in a year is pi times 10 to the 7th. So it's about 30 million seconds per year. So if you take 100 billion and divide it by 30 million, which is what the number of seconds in a year are, you would find out that it would take you 3,500 years just to count the galaxies in our observable universe. If you counted at a rate of one per second, so I'd say there's one, there's one, there's one, there's one. If I did that and counted all of the galaxies in the observable universe, and I never took a break from counting to sleep or eat or drink or use the bathroom or anything, then it would take me 3,500 years to count those galaxies. And then it would take another 3,500 years for me to count the stars in those galaxies. But what's worse than all that is the total number of stars being 10 to the 22. You can do another calculation. This is another Fermi type of calculation. And it turns out that the number of stars in the observable universe is also about the same as the number of dry grains of sand on all of planet Earth. So you might think, how in the heck did they come up with that one? Well, I've given you a way of how we came up with the 10 to the 11th galaxies, and I hinted a little bit at how we know there's 10 to the 11th stars on average in a galaxy. That's specifically for our galaxy, which is probably on the order of 400 billion, and the Andromeda galaxy is probably more like 8 or 900 billion stars, but that's our nearest big neighbor. But if you want to see how you actually estimate the number of dry grains of sand, is what you do is you go and look at a typical beach, and then you grab the grains of sand and you see that maybe the smallest is about a millimeter in size, maybe a half a millimeter, and the bigger ones are maybe up to 2 millimeters, and they're more like the rocky ones. So you take the geometric mean of that, and then you say, let's pretend this dry grain of sand is a sphere, and you calculate the volume of that sand. Okay, that's the volume of one sand grain. Now you say, okay, how far is it from the tide where the water's washing in up to the dune line on a beach? Well, you might estimate that the typical beach has a beach that is 100 meters wide, and the height of the beach at water level up to just before you get to the dune line is probably on the order of a meter or two. So you've now got a triangle that's 100 meters by 1 meter. And then you consider, what about a mile of beach? Well, a mile of beach would be 100 meters by 1 meter by 1 mile. So if you take 100 meters times 1 meter times the number of meters in a mile, okay, or you could do a kilometer, that would be much smarter. That would give you the volume of the sand, the dry sand on a mile of beach. Then you go and look up how many miles of beach there are on planet Earth, and Google will tell you that. And if you multiply that number of miles by the volume of that 1 mile, that'll give you the total volume of the dry grains of sand. Now you take that total volume and divide it by the volume of a single grain of sand, and lo and behold, the number you get is about 10 to the 22. So that's how we know that the number of stars in the observable universe is 10 to the 22nd. And you think, wow, that is huge. It's the number of dry grains of sand on planet Earth. That is ginormous. And then you think, okay, well, Mr. Younger has this 32-ounce cup packed full of water here I'm drinking. I promise it's not vodka. Right? So how do you think how many atoms or let's say molecules of water are in, let's say, a 16-ounce cup? Does anybody know that? Is that much bigger than 10 to the 22? Is that much smaller than 10 to the 22? Or is that about the same as 10 to the 22? Anybody know? I didn't expect anybody to know, by the way. That's the whole point. But I'm gonna get ready to blow your mind with this. Well, it turns out that a mole of water weighs about 18 grams. Okay, and a water has a density of 1 gram per cubic centimeter, and 16 ounces is about 250 milliliters. So with that calculation, you can see that evidently the number of molecules in especially this cup, much less a 16. I mean, a 16 ounce is not nearly as big, but for this cup, it's even bigger. But for a 16-ounce cup, that's going to have on the order of 100 times more molecules in it than there are stars on in the observable universe, and therefore more than 100 times more atoms slash molecules in a 16-ounce cup of water than there are dry grains of sand on planet Earth. Isn't that cool? All right, so that's just something that we do in our astronomy classes too. It's kind of fun, but it's a very typical technique that we need to understand to be able to function in the world and speak about things scientifically with precision and accuracy. If you'd like to learn more about that, there's a wonderful book called Physics and Technology for Future Presidents. One was written as a layman's book, and then another one he wrote, the same guy wrote another one that was actually used as a textbook for conceptual physics at UC Berkeley. His name's Robert Mullins, and he actually won the MacArthur Genius Award as well. He's also the person that the Koch brothers paid to do research on. He believed that the global climate data was erroneous because he specifically realized that people had put out all these temperature sensors all over planet Earth. And since they put them out, we've urbanized a lot of those areas so that now there's a lot more concrete and stuff like that all around. And that tends to make the area seem hotter. So he was guessing that this climbing of temperature that we were seeing was a result of all that urban sprawl. And he was afraid they weren't taking that into consideration. And he wrote papers on it. So the Koch brothers heard of this and they gave him a grant and said, "Hey, here's $200,000. I want you to go and research this claim and come back and report to us." And to their credit, Mullins said that specifically they never pressured him to say one thing or the other, but they did ask him to testify to Congress. So when he testified to Congress, he reported that he had discovered that in fact they were taking into account the urban heating, and in fact he had underestimated the amount of urban heating that they were experiencing, and they actually took it into account much more so than he would have, and from that they actually got way lower temperatures than he got. So what he learned was that the Earth had warmed up a lot more than they even thought, than even he had thought, for that matter. Okay, so that's the kind of person he is. But in that book and some other books he's written like that, they give you just a ton of information and tell you how to do these quick calculations. He tells you how to do quick calculations about like Hiroshima. How many people are going to get cancer as a result of Hiroshima. He can tell you how to do that calculation, or how many people are going to get cancer from having a head CT, or how many people are going to get cancer from having a, a lung CT, all that kind of stuff. That's the kind of approximations that you need to be able to do as a functional citizen on planet Earth, is what their argument is. All right. So I've got one more really cool example I want to show you with regards to estimating, and it's example 1.9. So let's do that now. And I'll read it to you. It says, example 1-9, estimate. Estimating the radius of the Earth. By the way, this is an extra credit assignment that you guys can do if you can find a lake or a part of the ocean front or any body of water that's on the order of 5 miles across or bigger. Then you can do this experiment yourself and turn it in, and I will give you extra credit for it. It's essentially could be a lab. So maybe if you have me for lab, which your class does, I could actually count that as an extra credit as a lab as well as a regular extra credit for homework. But here's what it is. It says, believe it or not, you can estimate the radius of Earth without having to go into space. See photograph on chapter 1. If you have ever been on the shore of a large lake, you may have noticed that you cannot see the beaches, piers, or rocks at water level across the lake on the opposite shore. The lake seems to bulge out between you and the opposite shore, a good clue that the earth is round, no matter what they tell you on X. The lake seems to bulge out, or excuse me, suppose you climb a step ladder and discover that when your eyes are 10 feet, about 3 meters above the water, you can just see the rocks at water level on the opposite shore. From a map, you estimate the distance to the opposite shore to be 6.1 kilometers with a height of 3 meters to estimate the radius r of Earth, or excuse me, use figure 110 with height h equals 3.0 meters to estimate the radius of the Earth. So let me draw that picture for you. So what we're imagining is this is a chunk of earth, and I'm not drawing it to scale, so it's going to look a little weird. But what we're doing here is this distance right here is one earth radius, and this is supposed to be a body of water right here. Okay. And this line right here is also one earth radius, just like this one is. Okay. But what we discovered was that, and actually I'm going to have to move this around a little bit, so let me move this down just a tad. Well, I didn't mean all that to happen, but here it is. We'll go with it. Okay, so I moved the whole thing down. Now, if you're able to stand up on top of this ladder, so here's a big ladder, and then you stand up on top of it like that, then what you can see is that this, and actually that line didn't draw quite as well. I'm trying to draw it tangential to the other side, but I'm also trying to draw it fairly straight. So I do like this. So I need to make my dude a little bigger, my dudemus. Okay, so here's my ladder now. And there's the person looking. What we discover here is that this height is h equals 3.0 meters. Now, I'm telling you that this is not the scale because in reality, this triangle would be super, 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 super narrow, and the height that h is would be itty bitty compared to the big radius r. So it turns out that this distance right here, which is supposed to represent this distance right here across the lake, is really, really close to the same measurement. Okay. So what we've done is we created a right triangle, and according to the Pythagorean theorem, we can have r plus h is the hypotenuse of this right triangle. So there's the right triangle, there's the right angle part of it. So the hypotenuse squared is equal to r squared plus this distance right here, which I'll call d. And actually, that's really unfortunate the way I wrote that. But this distance I'm going to call d. So r squared plus d squared is equal to r plus h squared. Now, we're making an approximation because that 6.1 kilometers is not exactly the distance across the lake, but it's pretty darn close because the scale is so small. So, what we can do is we can go ahead and say r squared plus 2rh plus 8 squared is equal to r squared plus d squared. And of course, the r squareds cancel on each side. And what we're trying to solve for here is really r. So now I have 2rh is equal to d squared minus h squared. And then that tells me r is equal to d squared minus h squared over 2h. So that's our actual formula for calculating the radius of the Earth. So now I can say the radius of the Earth is approximately equal to 6.1 kilometers squared. Now, if I want to use 6.1 kilometers, I can, but that means I'm going to have to convert the h to kilometers as well. So I'm not going to do that. I'm going to choose to use meters. So 6.1 kilometers becomes 6,100 meters. That's going to be squared minus 10 meters, or excuse me, 3 meters. It was 10 feet. Minus 3.0 meters squared divided by 2 times, in this case, I get the 3.0 meters again. So 6,100 squared, 6,100 squared minus 3 squared is just about 3.72 times 10 to the 7th divided by 6.0 meters. And this gives me 6.2 times 10 to the 1, 2, 3, 4, 5, 6 times 10 to the 6 meters is supposed to be the actual radius of the Earth. If you actually look up the radius of the Earth, okay, I'm typing when nothing's happening. The radius of the Earth is 6.378. This is the symbol, by the way, that they use for the Earth is R with a circle with a plus in it. It's 6.378 times 10 to the 6th meters. That's what the actual radius of the Earth is. So you can tell that basically I've got 6.3 uh, times 10 to the 6th minus 6.2 times 10 to the 6th. And now I'm going to divide that by 6.3 times 10 to the 6th. Oops. And that gives me about a couple percent error. So you guys can do this as well if you wish to. Last semester, I had a student do it from two places on the ocean front, and you're actually really lucky. You know, they were telling you to look it up from a map, but you can actually use Google Earth, and you can literally locate your spot on Google Earth by looking at Google Earth while you're at that spot. And then you can look at the spot that you're actually looking at. If someone else is there, you can look at it by where they are on Google Earth, and then you can stretch out a line from where you're at to where you're looking, and Google Earth will actually measure that in meters, kilometers, miles, whatever you want. So it's a pretty straightforward procedure, but you'd have to figure out some way to get up high and see where the water is touching, say, the dock that you're looking at or the bottom of the boat that you're looking at. A boat would be a problem unless it's docked up against a physical dock that's locked in place. But that's basically how you could do it. So if you guys want to do that, you're welcome to do that as a as two extra credit assignments. I'll count it as an extra lab, and I'll also count it as an extra homework. So, anybody have any questions on that one? All right. Well, we've completely finished chapter one now. So we're really done. We actually are supposed to have about 40 more minutes, and I don't really want to waste any time that we have. So I think I am going to at least get you started talking about chapter two, so we can get started next week and do more of this. But chapter two is called chapter two, describing motion kinematics in one dimension. And in order for us to make any sense of that, we need to figure out some stuff. So, for instance, the subsections of chapter 2 are 2.1, reference frames and displacement, 2.2, average velocity, 2/3 or 2-3 is instantaneous velocity, 2-4 is acceleration, 2-5 is motion at constant acceleration. 2-6 is solving problems. 2-7 is freely falling objects. And then 2-8 is variable acceleration integral calculus. Now, that section 2-8 has an asterisk by it. And most of the time, I skip the subsections that have asterisks by it. I did not skip it in chapter one, and I'm not skipping it in chapter two. Those are actually things you have to be able to do. So you do have to be able to do unit analysis or and/or dimensional analysis. Remember, the only difference is when all the calculations I showed you were using dimensional analysis, where the dimension of mass was capital M, the dimension of length was capital L, the dimension of time was capital T. If you're doing the same calculation using unit analysis, then the unit of mass is the kilogram, the unit of length is the meter, and the unit of time is the second. So you do all the same calculations except you're using a little m, a little s, or excuse me, a little k, g, a little m, and a little s. Okay. But we are also doing this variable acceleration integral calculus. So one of the problems you're going to have to be able to do is use calculus to solve basically two differential equations to come up with the position as a function of time if you're given the acceleration as a function of time, the initial velocity, and the initial position. If I give you the initial or the acceleration as a function of time, the velocity that the object has at time t equals 0, and the position that the object has at position t equals 0, then you can solve the two differential equations and actually determine what the integration constants are, and by that get an actual x of t, which is what we'd call the trajectory of the particle. So that's what we're doing with that. Now, what are we talking about in chapter 2? I also want to remind you, there is, like always, every chapter, there's a chapter opening question that you are supposed to answer before you go on and read the chapter. So make sure you do that, and make sure you even take the time in your notes while you're reading it to just jot down what you think the answer is. So when you read it later and you figure out what the real answer is, you can either pat yourself on the back for figuring it out, or you can figure out what your error was in making that assumption. And both of those are really helpful things, and it's more or less you using the scientific method to learn. So it's really, really helpful. For instance, this chapter 2 question is the following. It says, two small heavy balls have the same diameter, but one weighs twice as much as the other. The balls are dropped from a second-story balcony at the exact same time. The time to reach the ground below will be A, twice as long for the lighter ball as for the heavier ball, B, longer for the lighter ball but not twice as long, C, twice as long for the heavier ball as for the lighter one, D, longer for the heavier ball but not twice as long, and C, nearly the same for both balls. So if you've had a physics course before, or if you paid enough attention in like physical science in high school and whatnot, you probably can answer this. If you don't, if you can't, don't worry about it. It's not an insult, okay? We didn't necessarily learn everything we were supposed to learn when we went through grade school, and we certainly didn't learn everything we were supposed to learn when we went through, our first years of college. So it's perfectly fine. It's just another opportunity for you to do it over and over again till you learn. So make sure you do that question. It then talks about the studies of mechanics, dynamics, and kinematics. So I want to go ahead and open up with that and tell you that uh, what we're studying in 241 is essentially what we call classical mechanics. And we call it classical because in the the late 1800s, early 1900s, we discovered two major paradigms of physics that were completely out of the ordinary. Like if you'd interviewed all of the great scientists that were on planet Earth, say in the area around 1890, you would probably find that the vast majority of those scientists in the 1890s would have said, "We figured out the universe. We understand science so well that we really don't have anything else to look for. All we're going to do is continue doing predictions with that classical theory of mechanics that we learned from Newton and the classical electrodynamics that we learned from Maxwell and the classical thermodynamics that we learned from Joule and Maxwell and all these other people. And all we're going to do is a bunch of experiments to make sure that these theories are right, even to the third and fourth decimal place instead of just the first and second decimal place." They literally would have thought that. But it turned out there was like three or four really unanswered questions in the science world. One was this weird thing that when we shine light on a pure metal, uh, the light landing on the metal actually generates an electrical current that flows through the metal. It's called the photoelectric effect. And we understood how that could be because we understood electricity and magnetism as Maxwell had taught us with his four equations. We understood that well enough to recognize that light is a wave, and light being a wave means that a wave would be impending on a metal, and that those waves are electric fields oscillating in one plane and a magnetic field oscillating in a perpendicular plane, with the velocity being perpendicular to both those directions. And they were going to cause the individual atoms to polarize a little bit. So, for instance, when an electric field goes through and the electric field's pointing up, that's going to compel the electrons to try to move downward while the nucleus of the atom tries to move upward. And then when it gets to an electric field pointing down, it's going to flip the other way. So we could see that this going back and forth could, in principle, shake loose the electron, and the electrons moving through a metal freely is the definition of a current. So we knew that there was some understanding of it. But the problem was when we'd work out the physics of exactly what would happen, we'd expect there to be some kind of time delay, and we'd expect it to behave in very specific ways that the experiments were not agreeing with. So we had that problem to solve. We also had this weird problem going on where we could take like a glass test tube, specifically a closed test tube. If you imagine a double-ended test tube where, a test tube's normally got a rounded end and then open at the top. Imagine instead that you had two rounded ends and you just have sort of like a glass shaped like a pill, like a long, skinny pill. That's the kind of tube we're talking about. So if you make a test tube like that out of glass, and then you heat that glass up and put a little valve in it where you can suck all the gas out of it, and then also heat a spot up and put a little probe of metal in one end, and then heat a spot up on the other end and put a little probe of metal, we'll get basically two pieces of metal that can't touch each other, and they're a good distance away, like several centimeters, on the order of 10, 12, 14 centimeters, stuff like that. and then glass all surrounding it, and it had essentially a vacuum in it. But then we would backfill it with hydrogen gas, and then we'd backfill it with helium gas, and then we'd backfill another one with mercury gas, and another one with water vapor, and this sort of thing. Well, that is the predecessor to what we now know of as neon lights, like those shiny red lights you see at Krispy Kreme donuts, for instance. Any of the open signs that you see that glow in that reddish or orangish color. So that's what we're making. But that one, of course, it was called a neon light specifically because you would suck all the air out of it and then backfill it with neon gas. Well, it turns out that when you do that, when you make these tubes that are sealed up with a low pressure gas inside, if you put a really high voltage across that, it'll actually shine a light. It actually makes a light. That's more or less how the street lights work, at least the old street lights that you see. If you go into some parking lots of malls or shopping centers, you'll see some of the parking lots have this sort of bluish hue around them. Those are called mercury vapor lights. And then other ones you'll see, and they normally are accompanied by a hum. You'll hear a hmm, like fluorescent lights. That's very typical as well. But if you also look in parking lots of shopping centers, some of them have a sort of yellowish hue. Those are called sodium vapor lights, and they're made of a tube that's been evacuated, and then sodium gas has been put in there. So that's what they are. That's why they look yellow in the case of sodium vapor. That's why they look blue in the case of mercury vapor, because that is the characteristic colors of those glasses. But here's of those gases. So here's the weird part. When we did that with hydrogen, for instance, we could see a nice little reddish color light, not quite exactly red, sort of reddish orange. But if you take that light and let it go through a single slit, and then you take that light and send it through like a prism, you know what prisms do to light? They would take white light and turn it into a rainbow of colors. When we did that with this light, putting it through a prism, it would actually make, instead of a rainbow, it made like a black rainbow with just little stripes of color. So you'd have, instead of a whole rainbow that goes from red to orange to yellow to green to blue to indigo and violet all smoothly, you would have just individual slices of that rainbow showing up. And when you did it for hydrogen, you got very specific slices, like a red one, then an orange one, and then a yellow one, and then a long distance away, a blue one, something like that. Or actually, I think it was purple. Uh, we couldn't understand why those colors appeared, and we couldn't understand why it was specifically just a few colors. And then when we tried to do helium, we got entirely different lines. Those were all much more red, and there were a lot more of them. And then when we did, say, mercury vapor, it got really crazy. There was like 15 different colors and all this stuff. We did not understand why that was the case, but it was such a big deal that everybody had heard about it. There was a guy, I think his name was Balmer, if I remember correctly. It's either Balmer or Pashkin or another name that I can't remember right now, but I'm pretty sure it's Balmer. Balmer was a fairly famous mathematician who had a good career in physics and math, but he wasn't that necessarily well respected. He couldn't get a really good university job, so he's teaching girls. Okay, I'm being sexist here on purpose because that's the world that we lived in. But basically, someone who couldn't get a job at the university level that was quote unquote respected would then be forced to teach girls at a girl college or a girl school. And that's what he did. He was teaching at a girls' school, and he had figured out the actual wavelengths of those colors from hydrogen gas and used a curve fitting method to figure out an equation that gave you those exact colors. So this mathematician just on his own had worked out an equation for those colors, but the equation was purely like a curve fit, like, you know, like we do with Excel and stuff like that, a least squares fit. So it had no physical meaning. We didn't know why it worked. We just knew it worked. Well, what ultimately solved that problem and the photoelectric effect problem and another problem that Einstein and only Einstein saw was that Maxwell's equations would make a wave equation, and if you jump that wave equation to a frame that was moving at, let's say, half the speed of light, the equation didn't change at all. And that didn't make any sense to Einstein. There was a real problem. He was picturing all these paradoxes that would occur. Like if you rode in a train car traveling at close to the speed of light, you wouldn't be able to shave because you couldn't see the light bouncing off the mirror and hitting you back in your face and weird stuff like that. It was a rough approximation of what he said, but basically he found a lot of paradoxes. And the only way he could fix that paradox was to go on the assumption that the speed of light was a constant independent of the motion of the source of the light or independent of the motion of the source of the thing seeing the light. So if you imagine the car is the source of the light because it's got a headlight, if that car is moving at 3/4 of the speed of light, and then you try to measure the front of the beam as it comes to you, what Einstein's saying is even though that car is traveling at 3/4 of the speed of light and it's shooting out light that's traveling at the speed of light, you're going to measure the speed of light coming at you at the speed of light, period, not 1 + 3/4 of the speed of light. And if you are, in addition to that, running towards the headlight of that car at half the speed of light, it's still going to read the speed of light. So even though in that case it should have been about 2.25 times the speed of light, he didn't see that. So that was what compelled him to offer his special theory of relativity, which basically consisted of two postulates. The laws of physics are the same for all inertial observers. That's the first postulate. And inertial was just his way of getting rid of gravity. And the second one is the speed of light is a constant independent of the motion of the source and the motion of the observer. Those two principles, once you're someone like Einstein and can actually apply them, allow you to work out some very neat phenomena. For instance, time slows down when you're moving fast. And if you're moving fast, the dimension of the vehicle that you're in parallel to the motion will shrink so that like a big police car, which used to be those really long Lincoln town cars or whatever that they would use for police cars, those are big long Cadillac looking cars. If you travel in that car at 3/4 of the speed of light, its height isn't going to change. It's still going to be as tall as a Lincoln Continental or whatever, but its length is now going to be like the length of a Volkswagen Beetle. So that's called length contraction. And not only that, if you could watch that person driving by in that car and look at a little clock on his dashboard, you would see that the second hand is moving very, very, very slowly. However, if someone's in the back seat of that car with a telescope and they're looking at your clock, they would see your second hand going really slow and they would think their second hand is going the normal speed. So that's time dilation. That other thing is length contraction. But those three problems were what created special relativity, which was done completely by Einstein on his own, more or less. His wife actually contributed quite a bit, and he later divorced her. And as terms of his divorce, he said, "When I win the Nobel Prize, I'll give you the money." He wanted to get out from under this marriage. They had a child already. It's a really sort of sad story. This is the one instance where Einstein does not seem like the great kind-hearted person that he was. He was a real humanist, so he was one of the first people to stand up for race relations in America. In fact, he had when he was at Princeton University a famous black opera singer. I can't remember her name. I should know that history, but I've forgotten her name now. She came to New Jersey and was doing a show, and everybody just loved her. They went and watched and all this stuff, but she showed up at her hotel, and they wouldn't let her stay here because it was under Jim Crow laws, and she wasn't allowed to stay in the hotel with white people. So Einstein took her into his own house and let her stay with him. And he later wrote an essay saying, America is the greatest country I've ever been to, and it's probably the greatest country country there's ever been, but it has this one problem. It's got a problem with racism. So you can see he's a real human and really great in many ways. He says that we're not really humans until we can feel pain from anyone's death, not just the death of someone you know, stuff like that. But in this case, he ended up having a extremely special needs child. We think the child was mentally retard, what we would call retarded back then, very badly, and the child just disappeared. Probably what they did is they put him in an asylum and just left him and never thought about him. That was the common way of doing things back then. But that's a horrible thing to do nowadays. So you should sort of understand that that's a different time, but it is a horrible, horrible treatment. But anyways, that's what Einstein was, and that's the kind of person he was. He was overall a good person, but he was still a person of the times, just like, our founding fathers had slaves. They did, they supported slavery, that kind of stuff. So you just got to deal with that. But anyways, that all happened in this 1890 to 1930 era. By the end of 1930s, we actually had solved both problems. Like I said, Einstein had figured out the special theory of relativity with him and his wife, with a little bit of help from his wife. However, quantum mechanics turned out to be a lot bigger bugaboo. Planck solved the photoelectric effect by assuming that light would only come out in certain discrete packets of a fixed frequency, so that the energy was some constant times the frequency, or two times that constant times the frequency, or three times that constant times the frequency. And that was the only way he could understand. In that case, it wasn't the photoelectric effect, excuse me. That one was the dark black body radiation. Einstein solved the photoelectric effect, the one where light shines on a metal and creates a current. He was the second major paper of relativity. Planck did that first one on the black body radiation with the quantum hypothesis in 1901. Einstein in 1905 published about seven papers, five of which could have won him the Nobel Prize, and one of which did. The one that did win him the Nobel Prize was the photoelectric effect, because believe it or not, even though special relativity is now the most tested theory in the history of mankind, at the time, not a lot of people necessarily believed it was right. So they sort of looked at him as a bit of a nut for a little while, but eventually they figured out, oh yeah, he's right on the money. So he did special relativity, and that was not even big enough. In that specifically, after he sent the article in for publication, he sent the next day an addendum to it where he said, oh, by the way, I also happened to come up with this neat little equation, and it's the E equals MC squared equation, which that equation was what allowed us to go from not understanding how our sun could be more than 50,000 years old to what it is now. We now know our sun's about 4.5 billion years old, and that was all allowed because of Einstein's E equals mc squared. At the time, all we had was Lord Kelvin. Thomson was his name, but he was given a rank of Lord, and he became Lord Kelvin. And as Lord Kelvin, he had done a calculation where he said, okay, I know about the sun. I know roughly how massive it is. I know what its temperature is, that sort of thing. I also know the most powerful source of fuel we have is coal. So if the sun is made of that most powerful source of energy that we have, coal, then how long will it last? And when he did that calculation, he determined that the sun could be about 50,000 years old. That's about as long as it could live. If you go through our historical books, which is the Epic of Gilgamesh, which doesn't give us anything about dates, so that's not very helpful, but that's our oldest book. Our one of the oldest books is the books that now make up the Bible. And if you go through the book of Genesis, where they say Adam begot such and such a age, and then he begat such and such at such and such a age, and he begat such and such at such and such a age, if you add up all those times and assume, like the Bible tells you in the book of Genesis, that Adam came on the seventh day or whatever, or sixth day or whatever, if you calculate out how many years that is up until we know something that is historically fixed in time, which is the death of Nebuchadnezzar, then you figure out the earth has to be on the order of 10,000 years old. So if the sun can be calculated to live 50,000 years and the earth is only 10,000 years, everything's kosher. But in that time period, in the 1800s, is when we started to understand plate tectonics, when we started to see, remember, for instance, Charles Darwin and Abraham Lincoln were literally born on the same day. So that's how contemporary they are. And Charles Darwin was one of the people that told us about the theory of evolution. And the theory of evolution and plate tectonics, all that was coming together to suggest the Earth might be 100,000 years old, or maybe even 1,000,000 years old, right? And you can see, for instance, how the continents fit together, and when we ultimately measured how fast they're moving with respect to each other, we could even estimate how long ago they were together, and from that we could see that the Earth might be millions and millions of years old. But that left a gaping hole. How in the heck is the sun burning? Because if it's coal, it can only live for 50,000 years. In comes Einstein with this addendum to his paper, E equals mc squared. And lo and behold, what we discover is four hydrogens can run into each other. First, two of them run into each other, and one of the protons of the hydrogen atom spontaneously becomes a neutron, and the other one stays a proton, and it gives off some other particles to conserve energy and momentum and charge and stuff like that. And then that proton neutron pair will run into another proton neutron pair, and that'll actually make the nucleus of a helium atom, which is two protons and two neutrons. If you work out the physics of that collision, what you'll discover is the mass of the alpha particle, the nucleus of the helium atom, is actually less massive than the sum of the four masses of the protons that went in. That change in mass multiplied by c squared happens to be exactly the energy that comes out of the sun. And by that, you can calculate how many collisions or how many of those reactions must be occurring every second just by knowing how much energy is coming out of the sun. And lo and behold, we can now calculate that the Earth or the sun can probably live for about 11 billion years. All of that came from E equals mc squared. He also, by the way, wrote a paper on Brownian motion, which was the first definitive proof that that atoms existed. He literally proved the existence of atoms by calculating it theoretically using what we call statistical mechanics. And by doing it that way, the odds of him getting the right answer when it wasn't right, meaning that he made up something that wasn't fit, didn't fit reality, the odds of that are sort of like winning every lottery on planet Earth for every day that it's done for a whole year. In other words, it's longer than the age of the universe. So we had to definitively say, okay, his Brownian motion paper did show us that atoms existed. And he actually gave us approximations for how big they were. So that's a pretty amazing discovery. But that whole science that we're studying now, this 241 course, is all based on mechanics. It doesn't include thermodynamics, and it doesn't include electrodynamics, and it doesn't include what we call modern physics. That modern physics is nuclear physics, quantum mechanics, and relativity, not only special relativity, but general relativity. And it includes elementary particles, and it includes cosmology, all of which need relativity and quantum mechanics. So that's what we're studying now is mechanics as defined by Newton. And mechanics is broken up into two areas. There's the study of motion, just if you know a certain object has a certain acceleration and a certain initial velocity, you can use that to predict what its velocity will be later and what its position will be later and what its position will be some initially. All that stuff, that is called kinematics because we're studying the motion without trying to figure out what caused the motion. So that's called kinematics. That's what we're doing in chapters 2 and 3. And then there's a part of mechanics called dynamics, and that's the study of how we make the motions that occur. So that is, how did that object get that acceleration? Okay, now that we know that acceleration, the initial position, and the initial velocity, we can use kinematics to figure out what its velocity will be sometime later, what its position will be anytime later, and all that good stuff. But we needed mechanics, the dynamics portion of mechanics, to explain how it got that acceleration. So that's the two parts of mechanics is kinematics and dynamics, and we're focusing on the kinematics part right now. Anybody have any questions about that? Now, we're going to break down this motion into two different types. For instance, we might have this object, just a charging block, right? If I throw this, what's going to happen is this thing's going to fly like that. That's called translational motion. So translational motion is the whole object moving in some with some velocity, and it could be a velocity that changes and stuff like that. But the main thing is it's moving by itself through with some velocity in total. But in addition to that, there is rotational motion. So when I throw it, it's not likely that it's going to stay perfectly like this. It's probably going to do this as it moves through space. That's called rotational motion. We're going to first study translational motion as if everything we study is a point particle. But as time goes by, we'll eventually start to understand rotational motion, and then we can group those two together. So not only can I throw a BB, and if I know the angle at which I throw it relative to the horizontal, and I know the speed at which I throw it, then I can predict exactly how far it will go, how high it will go, what its speed will be just before it hits the ground, what its direction of speed will be just before it hits the ground, and when it will hit the ground. I can do all of that just with kinematics, just talking about translational motion. But I did it with a BB. If I threw this, it would be more complicated because it's not a single infinitesimally small BB. It has physical dimensions and it rotates. So it could hit the ground such that this corner is down, in which case it's going to hit way earlier than the center of mass, which could be represented by a little point right here in the middle, then that would occur. So we need to be able to group that rotational motion along with the translational motion so that we could imagine instead maybe throwing a pin, and we would keep track of not only where the center of mass of the pin is going, but where the tip is going with respect to it, so we'd know exactly its orientation at any point in time. We can't get to that part until we get to chapter, I believe it's chapter 10, where we start to study rotational motion. Okay. And then chapter 9 is momentum. And then chapter 11 is angular momentum. And then we go to simple harmonic motion in 14 and wave motion in chapter 15. And that's the stuff we're covering. So that's a little introduction to mechanics in general. I told you about a BB. That's something we call a point particle or just a particle. So your book talks about that too in this opening subsection, even before, excuse me, even before we get to section 2.1, we're talking about that. Then it goes into reference frames and displacement. So I'm going to talk about that real quick and then I'll let you guys go. So one thing you got to know is there's this famous statement that what was his name? Buckminster Fuller, the guy that came up with the idea of the Buckminster Fullerene, the carbon nanoballs, basically. So the big ball of carbon, that was Buckminster Fuller. And Buckminster Fuller said, we are traveling on spaceship Earth. And Carl Sagan, for instance, said, we are all star stuff. Both of those have big, big, big meanings that we need to understand as scientifically educated people. What Carl Sagan meant was the life cycle of stars are such that a star is born of just hydrogen and helium, and the hydrogen forming together to make helium, like I told you earlier with E equals mc squared. That's what actually makes the star burn. It's a nuclear reaction inside the core of it. And as the stars that are comparable in size to our sun itself, as those stars live, there's no circulation mechanism that allows the hydrogen and helium from the outer parts of the star to cycle in and out of the core. pretty much whatever you have in the core stays in the core, and whatever you have outside of the core stays outside of the core. So whatever area makes the core, and that's basically the area where the temperature is 10 million Kelvin or higher, in that area, however much hydrogen you has tells you how long your star can live, because constantly hydrogen is being transformed into helium, giving off energy, and then it doesn't circulate around, so the helium builds up inside. So as the star starts to run out of its lifetime, again, this is stars comparable to the size of our sun. If it's a star that's much smaller than ours, then it tends to actually have a circulation mechanism, and those stars can actually live way, 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 way longer than the big stars. But either way, as you start to run out of that hydrogen in the core, eventually you will run out to so much that it's not putting enough radiation pressure outward to keep gravity at bay. So gravity squishes that core. And when it squishes the core, it actually makes the temperature go up according to the ideal gas laws. That temperature going up can bring it from 10 million Kelvin to 100 million Kelvin. If it can really bring it up to that 25 or 100 million Kelvin, then there's another type of nuclear reaction that can occur, and the star can live a little bit longer. When it does that, we start fusing the helium in to make carbon and other stuff. And then when that new core starts to burn out because it's running out of helium, then if it's a big enough star, the gravity will crush it again and make it burn the next element and the next element and the next element, till what we end up having is like a gobstopper star. It's going to have the outermost inner layer is burning hydrogen into helium. Just inside of that is burning helium into carbon. Just inside of that is burning carbon into oxygen and nitrogen and some other things. And each layer goes to a different type of fusion. And then in the middle, we're fusing a bunch of different elements to iron. Well, it turns out iron is a dead end for nuclear fusion and nuclear fission. So when we start to build up iron in there, there's no way for the star to live any further. So eventually what happens is gravity gets so strong because there's not enough radiation pressure pushing out, because there's not enough stuff fusing in the innermost core. So it actually causes that innermost core to collapse. That creates a bunch of neutrinos, which we'll learn about later, and a massive explosion called a supernova explosion. Now, that supernova explosion is of a star that started off, at least in the first generation of stars, having only hydrogen and helium and a little bit of trace lithium, beryllium, and boron. So that was all the elements we had after the Big Bang. But in this first star exploding, it's going to explode and deliver carbon, which wasn't there, nitrogen, which wasn't there, oxygen, which wasn't there, and a bunch of other elements, including up to iron. All of those elements are now inside of that star that just exploded. So all of those elements are being blown all over space. Not only that, the energy of that collision is so high that it's brighter. That one star is brighter than the whole galaxy it's in. And that energy is so high, it can account for the other elements on the periodic table that we skipped and that we didn't get to. So that's where all the elements came from to make life. So if you have, for instance, anything higher on the periodic table than iron in you, then that particular material came from an exploding star. And that's why Carl Sagan said we're star stuff. Buckminster Fuller said we're traveling in spaceship Earth because the Earth turns out to be moving about 10,000 miles per second around our sun. It tends to rotate about 1,000 miles per second as a result of its rotation, and then our solar system turns out to be moving about 50,000 miles per second around the galaxy, and then our galaxy is moving at 100,000 miles per second, so on and so forth. So you can see everything at every level is moving. So there's no such thing as a sitting still rest coordinate system. So that's where I'm going to start off next time. I managed to do it without showing you any more equations or any more math. I just wanted to get you guys ready. So we'll start up there. It's now time for you to go. You're welcome to split. Make sure you chat me your first and last name before you split. I'm going to use that as roll, even though you're not required to come. This is a completely online class, but it helps me, and I'm supposed to keep track of your attendance. So please chat me your first and last name before you leave, but you're free to go, and I'll wait here till the last person leaves in case anybody has any questions. Thanks for coming, everybody. I'm sorry for being so long-winded. Thank you, Mihak. Thank you, Nathan. Do you
So I
have any?
do
Go ahead, Michael.
question. I'm a little confused on the labs
Okay.
as far as like where to attend or where to do them.
Gotcha. So, what I've decided to do is every Tuesday and Thursday at 8 a.m., whenever we have a lab, anyways, there will be some weeks where we won't have lab. I'm giving you that time to take your test, for instance. But every Tuesday and Thursday at 8 a.m., my intent is to do a intro to lab. So at that time, you'll I'll explain the lab document that I give you. I'll tell you what the process is that you got to go through to complete the lab, and it's all done online. So I want to remind you, in case you didn't see it in the syllabus or in case you didn't see it in the student handbook, online labs, some universities are not taking. So there's some chance that you might have to retake that lab when you get to a four-year institute. We're working on trying to get some online labs that we can definitely transfer and have them accept, but we're not there yet. So I want to give you that warning. But what we have is a bunch of labs, some of which you do by simulation software, other ones you do by us giving you the actual data, and then you compute it and analyze the data and stuff like that. This measuring of the height that you have to get up to see the other side of a lake, that could be a future lab. But that's the kind of lab stuff we'll do. So every Tuesday, I will introduce a new lab. I'll do it by Zoom meeting, and then I'll post that video to my YouTube channel, and it'll be up by 11:59 p.m. every Tuesday and Thursday. The lab that you do on Tuesday is due by 11:59 p.m. Tuesday the next week, and the lab that you do at 8 a.m. on Thursday has to be due by 11:59 p.m. on Thursday the next week as well. Okay.
Okay.
But basically, you don't have to show up to the Zoom meeting. I just make it so you'll have it there. And sometimes I just use videos that I did previously. But either way, I'll come in on at 8 o'clock and talk to you guys and tell you how to do it. And then I post it online. And then your job is just to download that Word document, type in any data that you're taking in a color color of font other than black. And if you handwrite something, that's fine. I don't mind it being black. But what I want to be able to do is when I look at that Word document as a PDF, you're going to turn it in as a PDF. But when you turn that document in, I want to be able to look at it and immediately tell by color or by handwriting that, hey, the student put this in and all this other stuff was already in the manual. And you're going to work out through that. And as you read the lab manual, if it asks you a question, you're supposed to click right to the right of the question mark, hit return, 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 then go in the middle of that white space and type in your answer to that question in some font other than black. And then you read some more. If you run into another question, you do it again. If you run into a procedure and it tells you to print something, what you're supposed to do is take a screenshot of that thing they wanted you to print and then paste it right there where they told you to print it, or paste it right there where they told you to make it. Same thing with data tables. And if they make you make, for instance, multiple graphs so that you can decide on which one you want to use, I would prefer you to turn in the other graphs that you make too, even if it doesn't say print. Okay. The other thing you have to do is every type of calculation you do in the lab, I need to see a sample calc of that. So, for instance, if in one part of the lab you take a mass and you measure it 5 times, then you're going to have to calculate the average of that mass, and that's going to represent the best estimate of the mass. So you need to show me a sample calculation of you calculating that average. But then if you get later on in the lab and you have to measure, say, a length, You're going to measure that 5 times, take an average. You've already showed me a calculation of average, so you don't have to show me that as a sample calc. But you did have to show me at least one of each type. Now, when you do that calculation, you can do it in hand and just take a screenshot of it and then put it right there in the lab where they tell you to do that calculation or where you learn that you have to do that calculation. You can typeset it if you want, but you don't have to. And if you do typeset it, you're gonna have to change the font color. So be careful of that. But
Okay.
literally every type of calculation you do, you have to do a sample calc for it. Go ahead. You were getting ready to ask me something.
No, no, I was just saying okay.
Okay. And you keep on and everything like that. You do all that those parts and you paste all those things in exactly where you're supposed to. I don't want at the end of the document all your lab or excuse me, all your graphs and all your calculations and all your tables. I don't want it. I want the actual graphs, the data tables, the calculations to be exactly where the procedure either told you to do it or asked you to do it. And then once you've done all that, put all that stuff in the Word document, you're going to do save as, and you're going to change the name of it to like, my name's Billy Younger. So I'd say Billy Y Lab 2 or something like that. That would be the name of the file. So I'd save it as a Word document as B Younger 2. And then I would do save as again. And this time I'd save it as a PDF. And that's what you got to turn in as a PDF.
Okay.
Okay, one big PDF document, not several of them, and all the stuff has to be in there and no typed black font.
Okay.
Okay.
Sounds
When
good.
you go to turn it in, you'll notice, like in this week 1 lab, you'll see there's something called Intro to Lab comments. I put that there because those are comments that I've made to students that turned in their labs in the past. So you can read over those and say, "Hey, it looks like I made that mistake, so let me go back and fix that." You should look at that before you turn it in. That way you won't lose, 5, 10, 15 points for little careless stuff. So that's why I put those there as often as I can.
Cool.
Okay. And the area that says lab 1, intro to lab, that's where you actually turn it in.
Okay.
All right.
Cool. Thank you.
And you can send me a text message if you have any other questions. You might not have been here last time, but that's more reliable for me to get than your emails. And when you do email me, you have to email me from your TCC web email account. You have to put your first and last name in it, and you have to write the subject line has to start with PHY on 241 OL for online. Okay.
Cool. Sounds good.
All right. Sorry for being so long-winded, but I wanted to make sure I told you
Oh,
everything.
no, thank you. Thank you. It was a great lecture.
All right. Thanks, Michael. I appreciate it.
Have a good one.
You too. Samuel, do you have a question, bud? I'm not sure Samuel's there anymore. Let me see if he types. He did not type. All right. Well, that's it, everybody. I'm going to stop sharing now, and our lab is over. Thank you for coming. Have a good evening. I hope to post this on my YouTube channel by tonight, but it might not be till tomorrow. Have a good day. Bye.